Hello and welcome to another deep dive. We are back in the world of chemistry today, specifically focusing on Unit 9. I want to start this off by asking you to, visualize something. Close your eyes for a second.
Unless you're driving or walking on the road, of course. Safety first.
Right, safety first.
Yeah.
But if you're at your desk, just picture yourself standing in the school chemistry lab. You know that specific smell.
I know it well.
Now look at your hand. You're holding a test tube. Inside, there's this distinct, heavy, oily liquid. It's yellow, maybe bordering on orange.
That would be nitrobenzene, a very classic, slightly intimidating starting material.
Exactly. It has that bitter almond smell, though you really shouldn't be sniffing it.
Please don't.
Okay, so now imagine you drop in a few pieces of tin metal, just some granulated tin, and you carefully add some concentrated hydrochloric acid to give it a little shake.
And things start to happen.
They really do. There's some heat, but a fizzing. But the most striking thing is the color. That sort of angry yellow starts to fade. It gets paler and paler until, well, the liquid becomes completely colorless.
It's one of the most satisfying visual changes, isn't it? It feels like you've really properly done some chemistry.
It does. But here's the big question. What just happened? We didn't just bleed through the color. We changed the entire identity of that substance.
And that visual shift is the hallmark of a chemical change. You have just witnessed the, let's call it magic, which is actually just rigorous science of preparing an amine from a nitro compound.
And that is our mission for today. We're exploring the preparation of amines. We're going to break down the how and the why of making these compounds, looking at sections B1 to B4 of our source material.
I'm glad you called it a mission, because really that's what it is. In the chemical industry, or even in our own bodies, making amines is a mission-critical process.
So you're saying amines are like a final product we need to manufacture?
Precisely. They are the building blocks for so many things. Medicines, polymers, dyes.
So today, we're putting on our manufacturer hats.
Yeah.
We're not just students memorizing lines. We are chemical engineers for a day.
That's the spirit. And to manufacture anything, you need two things: the right raw materials and the right tools.
Okay.
In our case, the raw materials are things like nitriles, amides, or that yellow nitro compound we just saw. And our tools, those are our reducing agents.
I like that framing. It shifts the mindset from, memorizing equations to building a product. It feels more active.
It is the best way to approach organic chemistry for the board exams. If you understand the tool and the raw material, you can predict the product. You don't have to just rote memorize every single reaction.
Okay, so let's establish that logic then. If we strip away all the complex names from a lithium aluminum hydride, all that, what is the one big idea at the heart of all these methods?
At the simplest level, preparing an amine is almost always about one single process: reduction.
Reduction. We hear that word constantly in chemistry. But in this specific context, making an amine, what does reduction actually mean physically?
Think of it like this. Reduction is the process of adding electrons or hydrogen atoms to nitrogen. Or, looking at it from the other side, it's about removing oxygen atoms from the nitrogen.
So we're either adding hydrogen or kicking out oxygen.
Exactly. I use the raw materials metaphor because in most of our starting compounds, the nitrogen is sort of locked up.
Locked up how? What do you mean by that?
Well, take a nitrile. The nitrogen is triple bonded to a carbon. It's held very tightly. Or look at a nitro compound. It's burdened by two heavy oxygen atoms. It's in a high oxidation state. It's oxidized.
So the nitrogen is either in a triple bond prison or it's carrying heavy oxygen baggage.
That's a very vivid way to put it, yes. And our job is to use our tools, the reducing agents, to liberate that nitrogen. We want to release it into its free, single-bonded, hydrogen-rich amine form.
That's a really helpful mental image. We're setting the nitrogen free.
You've got it.
Okay, so imagine you're in a chemical warehouse. You have these different piles of starting materials. One pile is nitriles, another is amides, a third nitro compounds. Your job is to look at the pile, pick the right tool, and turn that pile into the amine you need.
That's the perfect workflow. But to really master this, we need to zoom in. We have to look at what's really happening at the particle level, to the bonds.
Let's do that. Let's take the nitriles pile first. RC, triple bond, N. What's going on there?
So that triple bond is very strong. The nitrogen is sharing 3 pairs of electrons with carbon. To make it an imine, we need to break two of those bonds and add hydrogen atoms to both the carbon and the nitrogen.
We need to fully saturate it.
Exactly.
Yeah.
Now, contrast that with the nitro compounds pile. Note, here, nitrogen is bonded to oxygen, which is very electronegative. It pulls electron density away. The nitrogen is feeling very, electron deficient.
Being bullied by the oxygens.
In a way, yes. So the reducing agent's job is to forcefully push electrons back onto that nitrogen. This breaks the hold of the oxygen atoms, or the triple bond, and allows new bonds with hydrogen to form.
So whether we're breaking a triple bond or kicking out oxygen, the force doing the work is the flow of electrons from the reducing agent.
You've nailed it. And if we want to put this into an insert-safe definition, we would say, amines are commonly prepared by reduction of nitriles, amines, or nitro compounds using appropriate reducing agents, or by reductive amination of carbonyl compounds with ammonia or secondary amines.
That's comprehensive. But I want to pause here because I know this is where students start to get confused. There's a specific misunderstanding that happens right about now.
I think I know which one you mean, the one-size-fits-all idea.
Exactly. Students think, okay, reduction makes amines. So they assume any reduction method can make any type of amine primary, secondary, or tertiary.
And that is a dangerous assumption. We need to fix that right now.
Okay, let's lay down the rules.
Rule number 1. Reduction of nitriles, RCN, always, and I mean always, without exception, gives primary 1 degrees amines.
Always primary. Why is that structurally?
Because the nitrogen in a nitrile is at the end of the chain. C triple bond N. When you reduce it, you get CHNH. The nitrogen is only attached to 1 carbon. You physically cannot make a secondary or tertiary amine that way.
That makes sense. The nitrogen is terminal. It's at the end of the line.
Exactly. Now compare that to reductive amination. This is a different process where we react a carbonyl compound with, say, ammonia, and then reduce it. This method is incredibly flexible.
Flexible how?
Well, it can give you a primary, a secondary, or a tertiary amine. It all depends on what you start with. If you use ammonia, you get a primary amine. If you use a primary amine as your starting material, you get a secondary amine.
I see. So nitriles are a fixed path to primary amines. Reductive amination is like a choose-your-own-adventure.
That is the key distinction. Please keep that firmly in mind for your exams.
To help these concepts really stick, let's use an analogy. We mentioned tools before. Let's get a bit more artistic. Let's talk about the sculptor.
Ah, yes, the sculptor analogy. It's excellent for this. Imagine a nitrile, that RCN molecule, is a rough, hard block of stone.
Okay, I've got my raw stone.
Now, your reducing agent, let's say it's lithium aluminium hydride, LeHuber. That is your sharp, heavy-duty chisel.
Stone and chisel, got it.
The chisel chips away at the stone. In chemical terms, it's chipping away the extra bonds, the multiple bonds. It adds electrons to shape that stone into the final statue, which is our amine.
So just like a sculptor releases the statue that was hiding inside the stone.
The reducing agent releases the nitrogen from the prison of the triple bond.
Exactly.
Different starting materials, like amines, are just different shapes of stone blocks. But the chisel does the same fundamental job on all of them.
That's a beautiful way to think about it. Is there another way, maybe something a bit more everyday?
Well, there's always the kitchen. We can think of it as a cooking recipe. Your starting material, the nitrile, is the main ingredient. The reducing agent is the cooking method, like frying or baking. Different ingredients plus different methods give you different final dishes, or in our case, different amines.
Simple and intuitive. But I want to pull back for a second and ask something really fundamental. Why do we even need all these methods? Why can't we just find amines in nature?
That's a great question. The problem these methods solve is, well, scarcity. Simple amines don't really occur as standalone molecules that you can just dig up from the ground like you would coal or iron ore.
So we can't just go mining for methylion.
No. They're usually locked up in really complex things like proteins or alkaloids. They have to be synthesized. Without reduction, we simply couldn't make these fundamental building blocks in a lab.
And historically?
Oh, this was a massive breakthrough. In the 19th century, when chemists figured this out, it just opened the floodgates. Suddenly, they could create new medicines, new dyes, chemicals that just did not exist before.
So this chemistry is literally the foundation of the modern pharmaceutical and chemical industries.
Absolutely. It's our ability to build molecules from scratch.
I want to build a mental movie for everyone listening. Something you can recall in the exam hall when you're trying to remember which reaction is which.
Let's do it. Picture a vertical axis of line going straight up and down.
Okay, picturing it, a vertical line.
At the very top, place the nitro compound, NOA. Let's make it large and red. It's in a high oxidized state.
Top of the ladder, red, oxidized. Got it.
Now, Move down to the middle. Here we'll put the nitrile. C8A. Let's make this one yellow intense because it's trapped in that tight triple bond.
Middle run, yellow, tens.
And at the very bottom, we have our final product, the amine NEHO. Let's visualize this as cool green. It's free, it's stable, it's electron rich.
So red at the top, yellow in the middle, green at the bottom.
Now here's the key. Imagine a bright blue arrow labeled reducing agent. This arrow points only one way, downwards. It pushes the nitrogen from the red state at the top, or the yellow state in the middle, down into the green state at the bottom.
I can see it. The blue arrow is like a force pushing everything down to green.
That is the essence of an alkylmine preparation. You can visualize electrons flowing from that blue arrow into the nitrogen, stabilizing it and turning it green. It simplifies the whole chapter.
That's a powerful image. Everything wants to go down to green. Okay, let's move from mental movies back to the real world. We started with that lab visualization, the color change of nitrobenzene. I want to circle back to that.
The reduction of nitrobenzene with tin and hydrochloric acid?
We saw the yellow fade to colorless. You said that's the reaction happening.
Exactly. That no group is a chromophore. It creates color. The NHO group is not. When the yellow disappears, it's like a built-in progress bar telling you the reaction is complete.
That's convenient for the lab. But what if I'm running a huge chemical plant making tons of aniline for denim dye? Am I really using buckets of tin and acid?
Absolutely not. And this brings us to a crucial point. The technology application.
What's the difference?
In the lab, tin and HCl is fine. It works. But imagine the waste. For every kilo of aniline, you're generating kilos of tin salts and acid waste. It's messy and expensive.
Not very green chemistry.
Not at all. So for industrial aniline production, they use catalytic hydrogenation. They use hydrogen gas, H-Euro, and a metal catalyst like nickel or palladium.
And why is that better?
The byproduct is just water. It's cleaner, it's more economical, and it's scalable. You just pump in gas.
So for the exam, lab method is tin HCl. Industrial method is catalytic hydrogenation.
Correct. And a small expert tip. In the lab, we actually prefer using iron scrap and HCl over tin sometimes. It's a clever hack because the iron chloride product helps regenerate the acid, so you need less to start with.
Smart. Okay, I want to throw a curveball at you now. A counterintuitive example.
Go for it.
A student might think, okay, nitriles and nitro compounds are both high oxidation states. They're both at the top of that ladder, we imagine. So shouldn't reducing them give me the same kind of amine?
That is a very logical but incorrect thought. The answer is a hard no. And the reason is all about the carbon skeleton.
Skeleton.
Look at a nitrile, RCN. That carbon atom in the middle is part of the functional group. When you reduce it, that carbon doesn't vanish. It becomes a CH Euro group. So you end up with an anim that has one extra carbon atom in its chain.
So RCN becomes RCHN as the chain gets longer.
Exactly. We call it ascent of series. But now look at nitrobenzene, R. Oh no. The nitrogen is attached directly to the ring. There is no extra carbon atom in the nitro group. When you reduce it, the carbon skeleton stays exactly the same. You just get RNH.
That is a massive distinction. Nitriles extend the chain. Nitrile compounds preserve the skeleton.
You must count your carbons. It's the #1 rule. If a question asks you to convert, say, chloromethane to ethanamine, that's going from 1 carbon to 2, you have to go through the nitrile route. It's the only way.
That's probably the biggest trap in this whole unit.
It is where most marks are lost, for sure.
Which brings us perfectly to our exam-safe clarity lines. Let's nail down the specific rules our listeners need to have locked in.
Okay, clarity line 1. Reduction of nitriles, RSA, with Lyell H produces primary amines, RSA-H, with 1 additional carbon atom.
So that's your chain extender tool. Use it when you need to step up by 1 carbon.
Clarity line 2. Reduction of aromatic nitro compounds, RNLA-aros, with SNHCl or catalytic hydrogenation produces aromatic primary amines, RNHA.
The standard path to aniline. And remember, SNHCl is the messy lab method. H-catalyst is the clean industrial one.
Then clarity line 3. Reductive amination allows the preparation of primary, secondary, or tertiary amines.
So don't confuse this one. Nitriles give only primary. Reductive amination gives you choices. It's the flexible option.
And finally, clarity line 4. Lyell H is a strong reducing agent capable of reducing nitriles and amines.
Why is it important to specify Lyell H?
Because the choice of agent matters. Lyell H is the heavy artillery. A milder agent like sodium borohydride, NaBH, is great for other things, but it's too weak to break that tough nitrile triple bond.
So you can't just use any reducing agent. You need the sledgehammer for the nitrile.
Correct. If you write an ABH for a nitrile reduction in your exam, you will get 0 marks.
Good to know. This has been very productive. Let's do a quick, short recap to lock it all in.
Okay, let's sum it up. The core idea. Preparation of amines is all about reduction, adding electrons and hydrogen to nitrogen in nitriles, amides, or nitro compounds.
Remember the mental image. The blue arrow of the reducing agent, always pushing nitrogen down from the red or yellow oxidized states to the stable green amine state.
Recall the technology example. Industry uses clean catalytic hydrogenation with HEO gas, while the lab often uses messier methods with tin or iron and acid.
And finally, the most important exam tip. Count the carbons. Reducing a nitrile adds a carbon to your chain. Reducing nitrobenzene keeps the carbon count the same.
If you remember to count your carbons, you will avoid at least half of the common errors in organic synthesis questions.
So you now have the tools, the chisels, to build any amine you need. Whether you're extending a chain or making aniline, you know the path.
I would suggest maybe tonight just practice writing out the reactions for nitriles versus nitrile compounds side by side. Seeing it on paper really helps to lock in that difference.
Excellent advice. And here's a thought to leave you with. We've talked about amines as industrial chemicals, but remember, your brain is running on amines right now. Dopamine, serotonin. These are all amines. The chemistry we discussed today isn't just happening in a flask. In a very real way, it's happening inside you, allowing you to think and feel.
Chemistry is life, quite literally.
Good luck with your revision.
Keep learning.